Take a look around the room you're sitting in right now. There are walls on every side. You see them every day. You paint them, hang pictures on them, lean furniture against them, and probably never think twice about them. But here's a question. What would happen if all the walls in your house suddenly disappeared? At first, you might think, well, the roof would fall down. Maybe, maybe not. The truth is, walls do far more than most people realize. In fact, they are some of the hardest working parts of any building. They're constantly protecting you, supporting you, insulating you, and keeping you safe, all without drawing any attention to themselves. Today, we're going to look at the hidden engineering behind walls and why modern life would be almost impossible without them. Let's start with something simple. Imagine standing outside during a heavy rainstorm. The wind is blowing sideways, water is everywhere, the temperature is dropping. Now, imagine trying to live comfortably without walls. Not fun. One of the basic jobs of a wall is to separate the inside from the outside. Sounds obvious, right? But think about what that really means. A wall has to stop rain from getting in. It has to block cold air in winter. It has to keep hot air out during summer. It has to resist strong winds. It has to deal with sunlight, moisture, dust, insects, and sometimes even fire. Every single day, a wall is fighting a battle against the environment. And, unlike people, walls don't get weekends off. They're working 24 hours a day, 365 days a year. But protection from weather is only the beginning. Many walls are also carrying enormous amounts of weight. If you've ever seen an old brick building, chances are the walls themselves are supporting the floors and roof above. These are called load-bearing walls. In older buildings, the walls are often the skeleton of the structure. Everything depends on them. The roof pushes down, the upper floors push down. The walls transfer those forces all the way into the foundation and eventually into the ground. Without those walls, the building simply couldn't stand. That's why removing the wrong wall during a renovation can be incredibly dangerous. People sometimes think a wall is just a divider between rooms. Then they knock it down to create an open floor plan. Sometimes it works. Sometimes it turns into a very expensive mistake. Because some walls aren't just dividing space, they're literally holding up the building. Now, here's something interesting. Many modern skyscrapers don't rely on walls to carry most of the building's weight. Instead, steel frames and reinforced concrete structures do the heavy lifting. So, does that mean walls have become less important? Not at all. They've just taken on different jobs. In a modern office tower, exterior walls often act as protective shields. They're designed to keep out rain, reduce heat gain, improve energy efficiency, and provide comfort for the people inside. Some modern curtain walls are engineering masterpieces. A glass wall on a skyscraper might look simple from the street, but behind that glass are layers of technology designed to handle wind pressure, temperature changes, water penetration, and even earthquakes. What looks like a sheet of glass is actually a highly engineered system. Then there's another job walls perform that most people don't notice until it's missing: sound control. Imagine living in an apartment where you could hear every conversation from your neighbor, every phone call, every television show, every argument, every barking dog. That would get annoying very quickly. Walls help create privacy. They absorb, block, and reduce sound transmission. The thickness of a wall, the materials inside it, and even tiny construction details can make a huge difference in how much noise travels from one space to another. In many modern buildings, sound insulation is one of the most important design considerations. People may not notice good acoustics, but they definitely notice bad acoustics. Walls also play a major role in energy efficiency. Think about how much energy is spent heating and cooling buildings around the world. It's a massive amount. Without proper wall insulation, much of that energy would simply escape. In winter, heat would leak outside. In summer, unwanted heat would enter the building. Your heating and cooling systems would have to work much harder. Your energy bills would skyrocket. This is why modern walls often contain multiple layers. You might have structural materials, insulation, air barriers, moisture barriers, and interior finishes all working together. From the outside, it still looks like a simple wall. Inside, it's a carefully designed system. And then there's another job walls perform that most people don't notice until it's missing: fire protection. This is one of the most critical functions of walls. When a fire starts inside a building, walls can help slow its spread. They create compartments that prevent flames and smoke from moving too quickly. This gives people more time to evacuate and gives firefighters a better chance to control the situation. Many building codes around the world require specific fire-resistant wall assemblies. Some walls are designed to resist fire for 1 hour, others for 2 hours, some even longer. The goal is simple: contain the danger and protect lives. Now, let's step back and look at history. Humans have been building walls for thousands of years. Ancient civilizations used stone walls to protect cities. Farmers built walls to mark property boundaries. Families built walls to create shelter. Over time, walls evolved from simple barriers into highly sophisticated building systems. The walls in a medieval castle and the walls in a modern skyscraper may look different, but they share the same basic purpose. They create a safe, controlled environment for human life. That's actually one of the most remarkable things about architecture. At its core, architecture is about creating comfort in an environment that is often uncomfortable. Outside, there may be rain, heat, cold, wind, noise, and danger. Inside, there is shelter. And walls are one of the primary reasons that shelter exists. The next time you walk into a building, take a moment to think about what the walls around you are actually doing. They're holding back weather. They're controlling temperature. They're reducing noise. They're improving safety. They're protecting against fire. And, in many cases, they're helping support the structure itself, all while quietly standing in the background. Most people never notice walls because good walls don't demand attention. They simply do their job, day after day, year after year, decade after decade. That's what makes them one of the most underrated engineering achievements in the built environment. We rarely think about walls, but the moment they fail, everyone notices. And that's why understanding walls is really about understanding buildings themselves. Because long before we admire a building's shape, style, or appearance, its walls are already hard at work making everything inside possible.
Imagine you've just bought an old house. You walk inside, and the layout feels a little cramped. Small rooms, narrow hallways, walls everywhere. Then an idea pops into your head. What if I just knock down this wall and make the whole space open? It sounds simple. After all, it's just a wall, right? Well, maybe. Or maybe you're about to make the biggest mistake of your renovation project. Because not all walls are created equal. Some walls are basically room dividers. Remove them and the building won't care. Other walls are carrying thousands of pounds of weight every single day. Remove one of those, and you're asking for serious trouble. This is where one of the most important concepts in architecture and structural engineering comes in: the difference between load-bearing walls and non-load-bearing walls. Understanding this distinction is critical, not only for architects and engineers, but also for homeowners, contractors, and anyone thinking about changing a building. Let's start with load-bearing walls. A load-bearing wall does exactly what its name suggests. It carries loads. Think about everything sitting above the ground floor of a building: the roof, the upper floors, the furniture, the people, the equipment, even snow sitting on the roof during winter. All of that weight has to travel somewhere. Gravity never takes a day off. Every bit of weight is constantly pushing downward. A load-bearing wall acts like a vertical pathway that transfers those forces into the foundation and eventually into the ground. Without that pathway, the structure loses support. An easy way to picture this is to imagine a stack of books. If you place your hand underneath the stack, your hand supports the weight. Now remove your hand, the books fall. A load-bearing wall is essentially the building's hand. It's supporting everything above it. This system was common for thousands of years. Many ancient structures relied almost entirely on load-bearing walls. In fact, before steel and reinforced concrete became widely available, walls often served as both the enclosure and the structural framework. That's why old buildings frequently have extremely thick walls. The taller the building became, the thicker the lower walls had to be. Take a look at historic stone buildings or old brick apartments. Sometimes the ground floor walls are several times thicker than the walls on the upper floors. The reason is simple. The bottom walls must carry the accumulated weight of everything above them. The higher you go, the less weight there is to support. Now let's compare that with modern construction. Today, many buildings use structural frames made from steel or reinforced concrete. These frames carry most of the building's weight. Columns transfer loads downward. Beams distribute forces horizontally. The frame becomes the building's skeleton. As a result, many walls no longer need to carry structural loads. These are called non-load-bearing walls. Their primary purpose is not support. Their purpose is separation. They divide rooms. They provide privacy. They improve acoustics. They create functional spaces. You can think of them as the building's interior organization system. In many office buildings, nearly all interior walls fall into this category. That's one reason office layouts can be changed relatively easily. Walls can be removed, relocated, or rebuilt without affecting the building's structural stability. Of course, engineers still need to verify everything before changes are made. But generally speaking, non-load-bearing walls offer much greater flexibility. Now, here's where things get interesting. Just because a wall doesn't carry vertical loads doesn't mean it's unimportant. Some walls have another critical job. They resist lateral forces. In simple terms, they help buildings resist movement from the side. Think about strong winds. Think about earthquakes. Think about a tall building swaying during a storm. Those sideways forces can be incredibly powerful. A building must be able to resist them. This is where shear walls come into play. A shear wall is designed to resist horizontal forces. Instead of carrying weight straight down, it helps prevent the building from twisting, leaning, or collapsing sideways. You can think of a shear wall as a giant stabilizer. Imagine holding a deck of playing cards upright. Without support, the cards easily collapse sideways. Now imagine placing a stiff piece of cardboard along one side. Suddenly, the stack becomes much more stable. That's essentially what a shear wall does inside a building. Modern high-rise buildings rely heavily on shear walls.
In many skyscrapers, the elevator core and stairwell core are constructed from thick, reinforced concrete shear walls. These walls act as the backbone of the entire structure. They help the building stand firm against wind and seismic forces. Without them, many tall buildings simply wouldn't be possible. This is why identifying a wall's function can be surprisingly difficult. A wall may not appear important. It may look exactly like the wall next to it, but one wall could be carrying major structural loads while the other is simply dividing office space. Appearances can be deceiving. That's why structural drawings exist. Engineers don't guess. They analyze load paths, calculate forces, and determine exactly how a building behaves. Every structural element has a purpose. Unfortunately, not everyone appreciates that fact. Over the years, there have been numerous examples of people removing walls without understanding their function. Sometimes the consequences are minor. A few cracks appear. Doors stop closing properly. Floors become uneven. Other times, the results are catastrophic. One of the most famous examples is the Ronan Point collapse. While the causes involved multiple factors, the disaster highlighted how vulnerable buildings can become when critical structural elements fail. It served as a wake-up call for engineers and regulators around the world. Building safety standards improved significantly afterward. The lesson remains relevant today. Every structural component matters. Another common misconception is that thicker walls are always stronger. That's not necessarily true. A thin, reinforced concrete shear wall may be far stronger than a much thicker partition wall made from lightweight materials. Strength depends on design, materials, reinforcement, and engineering, not simply thickness. Modern buildings demonstrate this beautifully. A sleek glass tower may appear delicate from the outside, yet hidden behind the finishes are carefully engineered systems capable of resisting enormous forces. The walls, columns, beams, and foundations all work together as a single structural network. No element works alone. And that's really the key idea. Buildings are systems. Every load must have a path. Every force must be managed. Every structural component has a role. Some walls carry weight. Some walls divide space. Some walls resist earthquakes and wind. Some walls perform multiple functions at once, but none of them exist by accident. The next time you walk through a building, ask yourself a simple question. Which walls are merely separating rooms, and which walls are quietly holding up everything above your head? The answer isn't always obvious, but understanding that difference is one of the first steps towards understanding how buildings truly work. Because behind every wall is a story of engineering, physics, and design. A story most people never notice, yet one that makes modern architecture possible.
Few things make homeowners nervous faster than spotting a crack in a wall. You're walking through your house one day, coffee in hand, and suddenly you notice a thin line running across the paint. Maybe it wasn't there yesterday. Maybe it has been there for months and you just never paid attention. Either way, your brain immediately jumps to the worst possible conclusion. Is my house falling apart? It's a fair question. After all, buildings are supposed to be solid, walls are supposed to stay put, but when a crack appears, it feels like something has gone wrong. The interesting thing is that cracks are actually a normal part of building life. In fact, almost every building develops some cracks over time. The real question isn't whether a wall has cracks. The real question is why the cracks appeared and whether they're dangerous. To understand that, we need to understand a simple fact. Buildings move. That may sound strange because buildings look completely still, but they aren't. Every building on Earth is constantly moving, expanding, contracting, settling, and responding to its environment. Most of the movement is tiny, too small for us to notice,
but walls notice, and sometimes cracks are the result. Let's start with one of the most common causes of cracking: temperature. Think about a railroad track on a hot summer day. The steel expands as it heats up. The same thing happens to building materials. Concrete expands, steel expands, brick expands. Even materials inside your walls expand and contract as temperatures change. During the day, sunlight heats parts of a building. At night, temperatures drop. Summer brings heat. Winter brings cold. Year after year, these cycles repeat. The building is constantly breathing in and out, very slowly, very slightly, but over time, those movements create stress. When the stress becomes greater than what the material can comfortably handle, a crack forms. It's actually the building's way of releasing pressure. Another major cause is shrinkage. This is especially common in concrete. Many people think concrete becomes completely stable once it hardens. Not exactly. Concrete contains water when it's first poured. As it cures and dries, some of that moisture leaves the material. The concrete shrinks slightly. The amount may seem insignificant, but across a large wall, even tiny movements matter. If parts of the wall shrink differently, stresses develop. Eventually, cracks may appear. This is one reason engineers often include control joints in concrete structures. A control joint is basically a planned weak point. Instead of allowing random cracks to occur anywhere, the engineer creates locations where the movement can happen in a controlled way. In a sense, the building is given permission to crack in specific places. That sounds strange, but it's actually smart engineering. Now, let's talk about one of the more serious causes of cracking: foundation settlement. Every building sits on soil, and soil is rarely perfectly uniform. Some areas may be denser, some may contain more moisture, some may compress more than others. Over time, a building can settle into the ground. A small amount of settlement is completely normal. Engineers expect it. But problems occur when one part of the building settles more than another. This is called differential settlement. Imagine placing a table on an uneven floor. One leg sinks slightly while the others stay in place. The table twists. Buildings can experience something similar. When different sections move at different rates, walls are forced to absorb those movements, and walls don't always like that. Cracks begin to form around doors, windows, corners, and other stress points. This type of cracking often deserves closer attention because it may indicate ongoing foundation issues. Another common source of cracking is structural loading. Remember what we discussed in the previous chapter. Buildings carry weight, lots of it. As loads move through a structure, forces travel through beams, columns, slabs, and walls. Sometimes those forces create stress concentrations. A stress concentration is exactly what it sounds like. Instead of force being spread evenly, it becomes concentrated in a specific location. Door openings and window openings are classic examples. Imagine a solid wall. Loads are distributed relatively evenly. Now cut a large rectangular hole in that wall for a window. Suddenly, the forces must flow around the opening. The corners of the opening become areas of higher stress. That's why cracks often appear diagonally from the corners of windows and doors. Engineers understand this behavior and design reinforcement accordingly, but the physics never disappears. The wall is simply managing those forces as best it can. Then there are moisture-related problems. Water is one of the most persistent enemies of buildings. When materials absorb moisture, they often expand. When they dry out, they contract. Repeated wetting and drying cycles can create movement over time. In colder climates, things become even more challenging. Water can enter tiny cracks and pores. When temperatures drop below freezing, the ice turns into ice. Ice occupies more volume than liquid water. As it expands, it pushes against the surrounding material. This process repeats over and over.
Eventually, small cracks can grow larger. Nature is surprisingly patient. Give water enough time, and it can damage some of the strongest materials humans have ever created. Construction quality also plays a huge role. Even the best design can suffer if execution is poor. Improper curing of concrete, poorly installed reinforcement, inferior materials, inadequate workmanship, all of these factors increase the likelihood of cracking. A building is only as good as the people who build it. That's why quality control is such an important part of construction. Now here's the important part. Not all cracks are equal. Some are mostly cosmetic, others may indicate serious structural problems. Hairline cracks in paint or plaster are often harmless. Many occur naturally as materials age and settle. On the other hand, large cracks that continue growing, change direction suddenly, or appear alongside other warning signs may require professional evaluation. Particularly concerning signs include doors suddenly sticking, windows becoming difficult to open, uneven floors, walls separating from ceilings, noticeable leaning or displacement. These symptoms suggest that the issue may extend beyond surface finishes. This is why engineers don't judge cracks based solely on appearance. They look for patterns, location, width, depth, direction, growth over time. A crack is like a clue in a detective story. By itself, it may not reveal much, but combined with other evidence, it helps explain what's happening inside the building. In many ways, cracks are a form of communication. Buildings can't speak, they can't send text messages, they can't tell you when they're under stress, but they can crack. And those cracks often reveal valuable information about how the structure is behaving. The next time you notice a crack in a wall, don't panic immediately. At the same time, don't ignore it completely. Instead, think like an engineer. Ask why it appeared. What forces might be acting on the building? Is the crack changing? Is it isolated, or are there similar cracks elsewhere? Because every crack has a story. Sometimes that story is completely harmless. Sometimes it's a warning sign. But either way, cracks remind us of something fascinating. Buildings may look permanent and motionless, but they're actually living systems in constant interaction with the forces of the real world. And every now and then, a wall leaves behind a visible record of that struggle.
Imagine two houses sitting side by side on the same street. They're the same size. They look almost identical from the outside. Both have similar roofs, similar windows, similar floor plans. But when winter arrives, something strange happens. The first house stays warm and comfortable. The heating system barely works. Energy bills remain reasonable. The rooms feel quiet and cozy. The second house is a completely different story. Cold drafts seem to come from nowhere. The heater runs non-stop. The walls feel chilly to the touch. Outside traffic sounds like it's happening inside the living room. And somehow, every month, the utility bill gets more painful. So what's the difference? The answer often comes down to something hidden behind the paint and drywall: the wall system. Most people think of walls as simple barriers, a few layers of material stacked together, nothing particularly complicated. But modern walls are actually sophisticated engineering systems designed to solve multiple problems at the same time. They keep buildings warm, they reduce noise, they control moisture, they improve energy efficiency, and they help protect people during emergencies. Let's start with temperature. For most of human history, staying warm was a constant struggle. People burned wood, coal, or other fuels just to survive winter. Even then, many buildings remained cold and uncomfortable. The problem wasn't just producing heat. The problem was keeping the heat from escaping. Heat naturally moves from warmer areas to cooler areas.
It's one of the basic rules of physics. If your house is warm and the outside air is cold, heat is constantly trying to leave the building. Think of it like water leaking from a bucket. Unless you create a barrier, the heat keeps flowing away. This is where insulation comes in. Insulation slows down heat transfer. It doesn't create heat, it simply helps keep heat where you want it. Modern wall systems often contain layers of insulation made from materials such as fiberglass, mineral wool, rigid foam, or cellulose. These materials contain countless tiny air pockets, and air, surprisingly, is a very effective insulator when it's trapped. The goal is simple: keep warm air inside during winter and outside during summer. The result is greater comfort and lower energy consumption. But insulation isn't enough. Even a highly insulated wall can perform poorly if air leaks through it. Imagine wearing a thick winter coat with a giant hole in the back. The coat still contains insulation, but cold air can easily enter. Buildings face the same challenge. Tiny gaps around wall connections, windows, electrical penetrations, and construction joints can allow significant air leakage. This is why modern construction pays so much attention to air barriers. An air barrier acts like a windbreaker for the building. It prevents unwanted air movement through the wall assembly. When insulation and air barriers work together, the difference can be dramatic. The building becomes more comfortable, more efficient, and easier to control. Now, let's talk about something everyone notices immediately when it's missing: quiet. Imagine trying to sleep while hearing every car passing outside, every conversation from the apartment next door, every footstep from the hallway. Noise affects mood, concentration, productivity, and even health. That's why sound control has become a major focus in modern architecture. The interesting thing is that sound behaves differently from heat. Stopping sound requires different strategies. One effective approach is mass. Generally speaking, heavier walls block more sound. This is one reason thick concrete walls often provide excellent acoustic performance. The sound waves simply struggle to move the heavy material. Another strategy involves separation. Many modern walls contain multiple layers separated by air gaps. Instead of one solid barrier, the wall becomes a system of layers working together. When sound hits the first layer, some energy is absorbed. The remaining energy weakens as it travels through the airspace and additional layers. By the time it reaches the other side, much of the noise has disappeared. That's why a well-designed wall can make a busy city street seem surprisingly quiet from inside a building. But temperature and noise aren't the only enemies walls must fight. Moisture is another huge challenge. In fact, moisture causes more building damage than many people realize. Water can enter walls in several ways. Rain can penetrate exterior surfaces. Humidity can move through materials. Warm indoor air can carry water vapor into cooler parts of the wall. When moisture gets trapped, problems begin. Wood may rot, metal may corrode, mold may grow, insulation may lose effectiveness, indoor air quality may suffer. This is why moisture control is one of the most important aspects of wall design. Modern wall systems often include water-resistant layers, drainage planes, flashing details, and vapor control membranes. Each component serves a specific purpose. Together, they help keep the wall dry. A good wall doesn't just keep water out, it also manages moisture that inevitably finds its way inside. Engineers often say that water isn't the problem. Uncontrolled water is the problem. Now, let's move to one of the most critical functions of all: fire protection.
When most people think about fire safety, they think about smoke detectors and sprinkler systems. Those are extremely important, but walls also play a major role. During a fire, one of the biggest dangers is how quickly flames and smoke can spread. If fire moves freely through a building, evacuation becomes far more difficult. This is where fire-rated walls come into play. These walls are designed to resist fire for a specific period of time: 30 minutes, 1 hour, 2 hours, sometimes even longer. The goal is not necessarily to stop the fire forever. The goal is to slow it down. Every additional minute matters. A fire-rated wall can help contain a fire within one area while occupants escape and emergency responders arrive. Many fire-resistant wall systems use materials such as gypsum board, concrete, masonry, or specially designed insulation products. These materials help delay heat transfer and maintain structural integrity during extreme conditions. In a sense, fire-rated walls act like emergency shields. Most of the time, nobody notices them, but when disaster strikes, they become incredibly important. What's fascinating is that all these functions happen simultaneously. The same wall may be controlling heat, blocking sound, resisting moisture, and providing fire protection at the exact same moment. And all of that happens without anyone seeing it. From the room side, you simply see painted drywall. From the outside, you see brick, stone, glass, or cladding. The engineering remains hidden. But hidden doesn't mean simple. In fact, many modern wall systems are among the most carefully engineered parts of a building. Every layer exists for a reason. Every connection matters. Every detail contributes to performance. The next time you lean against a wall, remember that you're touching far more than a flat surface. You're touching an engineered system designed to create comfort, safety, efficiency, and protection. A modern wall isn't just dividing space, it's quietly controlling the environment around you. And when it's designed well, you hardly notice it's there, which is probably the highest compliment a wall can receive.
When people admire a building, they usually notice the big things: the overall shape, the height, the materials, the glass facade, the beautiful architecture. What they rarely notice are the tiny details hidden in corners, joints, and connections. Ironically, those small details are often the difference between a building that lasts for decades and one that develops problems after only a few years. In construction, there's a saying: buildings rarely fail because of the big parts. They usually fail because of the small details. And nowhere is that more true than in wall construction. A wall may be perfectly designed, the materials may be excellent, the structure may be strong, but if the connections around windows, doors, corners, and joints are poorly designed, problems can appear surprisingly fast. Let's start with one of the most vulnerable areas in any building: windows. Think about it. A wall is generally continuous and solid. Then suddenly, an architect cuts a huge hole in it. That hole becomes a window. From an engineering perspective, windows create several challenges at once. First, they interrupt the structural flow of the wall. Remember how loads travel through a building? Forces naturally move downward toward the foundation. When a window opening appears, those forces must travel around the opening instead of straight through it. That creates stress concentrations. Engineers solve this problem using a structural element called a lintel. A lintel is essentially a beam placed above the window. Its job is simple: carry the weight above the opening and transfer it safely to the wall on both sides. Without a lintel, the masonry above the window could crack or even collapse. You can think of it like a bridge. Instead of cars crossing a river, structural loads are crossing a window opening.
The principle is exactly the same. But structural support is only part of the story. Water is often a much bigger enemy. Rainwater constantly attacks exterior walls. Gravity pulls water downward. Wind pushes it sideways. Surface tension allows it to sneak into surprisingly small gaps. A poorly designed window connection can become a direct invitation for water intrusion. And water is patient. It may take months, sometimes years, but eventually moisture finds weaknesses. This is why flashing is so important. Flashing is a thin, waterproof material installed around openings and transitions. Its purpose is to guide water away from vulnerable areas. Think of flashing as a traffic control system for rainwater. Instead of allowing water to wander wherever it wants, flashing directs it safely outside the building. Good flashing is invisible when everything works correctly. Bad flashing becomes very visible when leaks start appearing. That's why experienced architects often pay obsessive attention to window details. A tiny mistake can lead to expensive repairs later. Now let's move to doors. At first glance, doors seem simpler than windows. After all, they're just openings that people walk through. But from a construction standpoint, doors create many of the same challenges. Like windows, doors interrupt the wall. Like windows, they require structural support above the opening. And like windows, they must resist water and air infiltration. However, doors face an additional challenge: movement. Unlike windows, doors are constantly opening and closing, thousands of times, sometimes tens of thousands of times over their lifespan. Every movement creates wear. Every movement tests the seals. Every movement creates opportunities for air and water to enter. That's why the details around door frames, thresholds, and weather seals are so important. A well-designed door should close tightly while still operating smoothly. Sounds easy. In reality, it's a surprisingly complex balance. Now let's talk about corners. Corners might seem boring. Most people never think about them, but engineers do, a lot, because corners are places where forces change direction. Materials meet, movement occurs, and stress often concentrates. Imagine folding a piece of paper. The fold line experiences more stress than the flat surface. Buildings behave similarly. Corners often become areas where cracks first appear. This is especially true when different materials meet: concrete and brick, steel and masonry, wood and drywall. Each material expands and contracts differently. Each responds differently to temperature and moisture. If these movements aren't properly accommodated, cracks become almost inevitable. That's why expansion joints and control joints exist. These joints allow buildings to move slightly without causing damage. And yes, buildings are constantly moving. Not enough for you to notice, but enough that engineers must account for it. A building that cannot move is often a building that will crack. Then there is the area where the wall meets the ground. This region is known as the base of the wall, and it's one of the harshest environments in the entire structure. Think about everything happening there. Rain splashes upward from the ground. Moisture rises from the soil. Snow accumulates. Salt may be present. Lawn equipment may strike the wall. People walk nearby. Pets brush against it. It's a tough place to be. This is why architects often design a special lower section known as the plinth or base detail. The materials near the ground are usually more durable and moisture-resistant than those used higher up. Stone, concrete, and other robust materials are common choices. The goal is simple: protect the most vulnerable part of the wall. Now let's move upward. What happens where the wall meets the roof? This connection is another critical detail. When rain falls on a roof, enormous amounts of water can be collected and redirected. If roof-to-wall connections are poorly designed, leaks become almost inevitable. Proper flashing, drainage systems, waterproof membranes, and careful detailing are essential. Many roof leaks don't actually originate where the water appears inside. Water often travels considerable distances before becoming visible. That's what makes diagnosing leaks so challenging. The source and the symptom may be far apart. This is one reason experienced building inspectors spend so much time examining connections and transitions. They know that buildings are rarely challenged by large, obvious openings. The real battle occurs at the joints, at the edges, at the places where one material meets another. What makes modern construction fascinating is that these details are becoming increasingly sophisticated. Today's buildings must meet strict requirements for energy efficiency, weather resistance, fire safety, durability, and occupant comfort. Every connection has to perform multiple functions simultaneously. A window detail may need to manage structure, moisture, air leakage, thermal performance, and appearance. That's a lot to ask from a few inches of construction. Yet modern buildings accomplish this every day, and most people never notice. Which brings us to one of the most important lessons in architecture. Great buildings aren't defined by their biggest features, they're defined by their smallest details. Anyone can draw an impressive building. Creating one that survives decades of weather, movement, moisture, and daily use is much harder. The next time you walk past a building, take a closer look. Notice the corners. Look around the windows. Examine the door frames. Pay attention to where different materials meet, because that's where some of the most important engineering decisions are hiding. And those tiny details often determine whether a building remains beautiful and functional for 50 years or starts developing problems long before it should.
If you could travel back in time 1,000 years and ask a builder what a wall was, the answer would be simple. A wall was something thick, something heavy, something made from stone, brick, mud, or timber. Its job was straightforward: hold up the roof, keep out the weather, protect the people inside. For centuries, that basic idea hardly changed. The thicker the wall, the stronger it was believed to be. The heavier the wall, the safer it felt. And for a very long time, that approach worked. But then, something remarkable happened. Buildings started growing taller, much taller. Instead of 3 stories, instead of 5 stories, cities began building structures dozens and eventually hundreds of stories high. Suddenly, the traditional idea of a wall no longer made sense. Imagine trying to build a 100-story skyscraper using only load-bearing brick walls. The walls at the bottom would need to be incredibly thick. Some estimates suggest they would need to be several meters thick just to support the weight above. The lower floors would look more like a fortress than an office building. It simply wouldn't be practical. The skyscraper revolution required a completely different way of thinking, and that changed the role of walls forever. Instead of carrying most of the building's weight, walls gradually became protective skins wrapped around structural frames. Steel and reinforced concrete became the skeleton. Walls became the enclosure. This shift led to one of the most important innovations in modern architecture: the curtain wall. The name sounds dramatic, but the concept is surprisingly simple. A curtain wall is an exterior wall that does not carry the building's structural loads. Instead, it hangs from the building's frame, much like a curtain hangs from a rod. The structural system supports the building. The curtain wall protects the interior environment. This idea transformed architecture. For the first time, architects were no longer limited by thick masonry walls. Large areas of glass became possible. Buildings could appear lighter, more open, and more transparent. Entire skylines changed. Cities began filling with glass towers that would have been impossible just a century earlier. Walk through the financial districts of major cities today, and you'll see countless examples. The walls no longer look like walls at all. They look like giant sheets of glass stretching towards the sky. But appearances can be deceiving. Modern curtain walls may look simple, but they're among the most sophisticated systems in the entire building. Think about everything a skyscraper facade must endure: strong winds, heavy rain, extreme temperatures, thermal expansion, building movement, ultraviolet radiation, air pressure differences, and in some regions, earthquakes. The wall must handle all of this while remaining watertight, energy efficient, durable, and visually attractive. That's an extraordinary engineering challenge. In fact, tall buildings don't stand completely still. Many people are surprised to learn this. During strong winds, skyscrapers can sway several feet at the top. Occupants may never notice, but the movement is real. The wall system must be flexible enough to accommodate that movement without cracking or leaking. Imagine trying to build a giant glass shell around a structure that's constantly moving. That's exactly what facade engineers do. And as impressive as today's walls are, the future looks even more fascinating. For decades, walls were mostly passive. They simply separated the inside from the outside. Now they're becoming active systems. One major trend is the rise of high-performance facades. Traditional walls tried to block heat transfer. Modern walls actively manage it. Advanced glazing systems can reduce solar heat gain while still allowing natural daylight inside. Some glass coatings are nearly invisible, yet dramatically improve energy performance. Others can reflect specific wavelengths of sunlight while allowing visible light to pass through. The result is more comfortable buildings and lower energy consumption. Then there's smart glass. This technology feels almost futuristic. Imagine a window that automatically changes its tint depending on sunlight conditions. Bright afternoon sun arrives, the glass darkens. Clouds move in, the glass becomes more transparent again. No blinds, no curtains, no manual adjustments. The wall itself responds to environmental conditions. Some buildings are already using versions of this technology today, and the technology continues to improve. Another exciting development is the integration of renewable energy into wall systems. Traditionally, solar panels were installed on roofs, but roofs have limited space. Walls, on the other hand, provide enormous surface areas. Engineers are now developing building-integrated photovoltaic systems. In simple terms, the wall itself generates electricity. Parts of the facade become miniature power plants. Imagine a skyscraper producing energy from its own exterior surfaces throughout the day. That's no longer science fiction. It's already happening. Sustainability is also reshaping how walls are designed. The construction industry is under increasing pressure to reduce carbon emissions. As a result, architects and engineers are exploring new materials and construction methods. Mass timber is one example. Engineered wood products are being used in increasingly large buildings. These materials can store carbon while offering excellent structural performance. New insulation materials are becoming thinner and more efficient. Recycled materials are finding their way into wall assemblies. Entire wall systems are being optimized to reduce environmental impact. And then there's the rise of prefabrication. Traditionally, walls were built piece by piece on construction sites. That process was slow and highly dependent on weather and labor conditions. Today, many wall systems are manufactured in factories. Entire facade sections arrive at the site already assembled. Workers simply lift them in place.
This approach improves quality control, reduces waste, and speeds up construction. Some modern towers can install entire floors of exterior wall systems in just a matter of days. The efficiency gains are remarkable. Looking even further ahead, researchers are experimenting with truly intelligent building envelopes. Future walls may contain sensors that continuously monitor temperature, moisture, air quality, structural performance, and energy usage. The wall could detect problems before humans even notice them. That's the direction many technologies are heading. Some researchers are even exploring self-healing materials. These materials can automatically seal tiny cracks when damage occurs. The concept sounds almost impossible, yet prototypes already exist. A future wall might repair minor damage on its own, without human intervention. The evolution of walls tells an incredible story. Thousands of years ago, walls were little more than stacked stones protecting people from the elements. Today, they're highly engineered systems that manage heat, sound, moisture, energy, safety, and environmental performance, and they're continuing to evolve. The most interesting part is that walls are becoming increasingly invisible. Not physically invisible, but functionally invisible. When a wall performs perfectly, you don't think about it. You stay comfortable, you stay safe, you enjoy natural light, you save energy, you remain protected from weather. Everything simply works. Behind that effortless experience is centuries of innovation, engineering, and design. So the next time you look at a modern skyscraper covered in glass, remember this: you're not looking at a simple wall. You're looking at one of the most advanced pieces of engineering in the entire building. And the walls of the future may be even smarter than we can imagine today. Because while walls have always protected us, they're gradually becoming something much more than barriers. They're becoming active partners in how buildings function, perform, and interact with the world around them. And this transformation is only just beginning.